Welcome. In this lecture, I want to talk about what it means for a function to be continuous, which you can kind of think of as you've probably heard from back in your youth, that it means that you could draw the graph with a pencil without ever picking up your pencil. But let's kind of go a little bit more formally, because it gives you something to work with if you're trying to show that something is not continuous or that it is continuous, something a little bit more formal. Okay, so formally, what do we have? So we have a function f. So this function f is going to be what we call continuous. So is continuous and then right now we're going to talk about it being at a particular point. So this is going to be at the point x equals a, or the x value. So at the input x value, so x equals a. Okay, so when is this going to be true? So when is the function f continuous at x equals a? So two things have to be true. So the first one is that we need that this function f is defined. So f of x has to actually be defined at x equals a. So is defined at this value x equals a. Okay, so we can stick x equals a into the function f and get an output, a finite output. Okay, and then the other part, a single finite output. And the other part of it that we actually need is that we're going to have these limits, and I'll draw a picture so that'll hopefully make this make a little bit more sense. So we have this limit we have as x goes to, and then we're going to a from the left-hand side, so like this. And we're going to take our value f, right? And so we're looking at putting in values of x into here. Okay, and those x values are approaching a from the left-hand side. And what we want to get is we want to get that this is equal to what would happen if we actually stuck this value a into my function. And then I want at the same time that that's going to equal what I'm going to get if I'm going to take this limit as x approaches a from the right-hand side of f of x. Okay, now, what is kind of the picture of this? So let's say we have our x-axis here. And just for simplicity, I'm going to have, I'm going to write x equals a here, and I'm going to pretend that the entire graph of the function is above the x-axis. It doesn't really matter. In fact, maybe I won't, just to make it a little bit more clear. It doesn't necessarily need to stay above that axis. I'm a little concerned that that's not very visible. Let's just go a little bit darker. Okay, so then what do we want to have happen? We want to look at what happens. So this is y equals f of x. And I'm going to want to look at what happens as, so we want to look at what happens as x approaches from this side, right? So we want to approach from this side. We want to approach from this side. And so what you're going to be looking at is these values. So I have my value here, right? Kind of this height here is going to be my value. So this is my f of a. Should be an a there. So that's my f of a there. And then I'm going to be looking at these values, right? So what's going to happen? I'm looking at my values as we approach from this side. Okay, so I'll do this with a different color so we have what are happening to my f values as I put in x values that are closer and closer to a but are less than a. Okay, so these are my values of f as x approaches a from the left-hand side. So here I have values of f as we have that as my x values approach, so a from the left-hand side. So I want those to close in on this value, and I want the same thing to happen on the other side. So these are going to be my values of f values of f, and now we have as x approaches, so as x approaches a from the right-hand side, okay? And then we have our values, so then at the same time we're going to have our values here. So this is our value of f at x equals a. So now we're actually at this x equals a. So there are three kinds of different values. I'm looking at the values that are, the values of f as x approaches a from the left-hand side, or from values of x that are less than a. I have the value of f precisely at a, and then I have the values of f that I get as x approaches a from the right-hand side, or from values of x that are greater than a. And those three values should all be the same. Okay, so those limits exist, and they should be the same. Okay, so the point here is that these should all be the same. So these values and these values and these values should all be the same. Okay, so should all be the same. Okay, so that's what it means to be continuous, is that you can really predict what your function is going to be by looking at it, what it does nearby the particular value that you're looking at. Okay, and then we would say that f, so f is continuous, and then f is continuous if it is continuous, so means that f is continuous at every x equals a in its domain. So f is continuous at each x equals a in its domain, right? So then it's continuous on its domain. It's continuous where it's defined. Okay, so continuous functions, this is just a little bit of formalization of what you've seen before. It just means that you can draw the graph without picking up your pencil. Okay, so I hope that made some sense, and I will see you in the next lecture.